What specific problem does your proposed method address in the realm of reasoning capabilities in language models, and how does it differentiate from traditional methods?
The proposed method addresses the limitation of traditional language models that rely on fixed-depth architectures and long-context reasoning, which often require extensive training on bespoke data and can be inefficient in terms of memory and computation. By introducing a latent depth recurrent architecture, the model can perform an arbitrary number of computations before emitting a token, allowing for more flexible and efficient reasoning. This approach enables the model to utilize standard training data without the need for specialized demonstrations, thus reducing the memory footprint and enhancing performance at test time through recurrent reasoning in latent space. Unlike traditional methods that project internal reasoning down to a single verbalized token, the recurrent mechanism allows for complex, iterative computations that can capture nuanced reasoning behaviors, such as spatial thinking and physical intuition. Overall, this method not only improves the model's reasoning capabilities, but also provides a scalable alternative to enhance performance without the need for larger parameter counts or extensive training data.
How does the proposed algorithm work? Illustrate the process step by step, from input token embedding through the recurrent processing to output generation.
The proposed algorithm begins with input token embedding, where the input tokens, X, are embedded into a latent space using a prelude block that applies multiple transformer layers, resulting in an embedded representation, E. Next, the core recurrent block, R, processes this embedded input iteratively. It takes the previous latent state, S_I1, and the embedded input, E, to produce a new latent state, S_I, through a series of transformer layers. This process is repeated for a randomly sampled number of iterations, R, allowing the model to perform multiple computations before generating an output. After completing the recurrent iterations, the final latent state is passed to the coda block, which processes it to produce the probabilities of the next token. This architecture enables the model to leverage recurrent reasoning in latent space, enhancing its ability to handle complex tasks and improving performance through additional compute at test time.
Can you provide a concrete example demonstrating the mechanism of your algorithm, walking through its main steps with hypothetical input?
To illustrate the mechanism of our recurrent depth language model, consider a hypothetical input sequence of tokens representing a mathematical problem. The model begins by embedding these tokens into a latent space using the prelude block, which processes the input through multiple transformer layers. Next, the core recurrent block is activated, where the model initializes a latent state, S_0, from a random distribution and iteratively updates this state through R iterations, incorporating the embedded input, E, at each step. For instance, if the model is set to run for 32 iterations, it will repeatedly apply the transformation S_I equals RE S_I1 for I, from 1 to 32, allowing it to refine its understanding of the problem through recurrent reasoning. Finally, after completing the iterations, the coda block processes the last latent state, S_R, to produce the output probabilities for the next token, effectively generating a response that reflects a deep iterative reasoning process rather than a simple memorization of patterns.
What are the primary advantages of using recurrent depth models over conventional chain of thought models? Please discuss both theoretical and practical aspects.
The primary advantages of using recurrent depth models over conventional chain of thought models lie in their efficiency and flexibility in reasoning. Theoretically, recurrent depth models allow for an arbitrary number of computations before emitting a token, enabling them to perform latent reasoning without the need for bespoke training data, unlike chain of thought models that require extensive domain-specific demonstrations. Practically, this results in lower memory requirements during training and inference, as recurrent models do not necessitate long context windows, which are essential for chain of thought reasoning. Additionally, recurrent depth models can adaptively scale their compute at test time, enhancing performance based on the complexity of the task, while chain of thought models are limited by their fixed inference structure. Overall, these models exhibit improved computational efficiency and the ability to learn complex reasoning behaviors, making them more adept at handling diverse tasks.
How did you validate the performance of your model, including the datasets used, metrics for evaluation, and benchmarks you compared against?
To validate the performance of our model, we trained it on a mixture of datasets heavily skewed towards code and mathematical reasoning, supplemented with general web text to ensure standard language modeling abilities. We executed evaluations against established benchmarks, including standard language tasks and specific math and coding challenges, using the LM-Eval harness and BigCodeBench for coding benchmarks. Our model was compared to other open-source models, such as Amber and Pythia, as well as Olmo variants, focusing on metrics like performance on GSM-8K and math for mathematical reasoning, and MBPP and HumanEval for coding tasks. We also conducted a direct comparison between our recurrent model and a non-recurrent baseline, revealing that the recurrent model significantly outperformed its counterpart, particularly on more complex tasks. The results indicated that our model's performance improved with increased test time compute, showcasing its potential for reasoning tasks.
What were the key results achieved with your recurrent depth model, and how do they compare to existing models in terms of performance and computational efficiency?
The key results achieved with our recurrent depth model include significant performance improvements in mathematical reasoning and coding tasks, where it outperformed all other general-purpose open-source models, except for the latest Olmo 2 model in math benchmarks. Specifically, on the GSM-8K and math datasets, our model demonstrated superior capabilities, achieving a 5-fold improvement over a non-recurrent baseline at an early training stage. In terms of computational efficiency, our model, with only 3 5B parameters, consumes raw flops comparable to a 32B parameter transformer during pre-training, while maintaining the ability to scale performance with test time compute, effectively competing with models that have much larger parameter counts. Additionally, the recurrent architecture allows for adaptive compute at the token level, enabling the model to exit early on easier predictions, which enhances efficiency without sacrificing performance. Overall, our recurrent depth model not only matches but also exceeds the capabilities of existing models, particularly in complex reasoning tasks, while being more efficient in its computational resource usage.